going to talk about programming assistance for TypeScript.
All right, thank you very much. Just make sure we're good on tech here. Hope everyone's doing well. So, the way I want to start off my talk is I just want to start with something we hope we all believe in. And so probably one of the reasons why we love functional programming, in particular type functional programming, is that phrase there. You probably all mentioned it, probably muttered it at some time in your life when, oh wow, my types are so awesome that my program just writes itself. And so what I want to spend kind of the majority of the talk talking about is deconstructing that a little bit to kind of motivate the work that I'm going to be showing you today. All right? And so what does it mean that my program writes itself? Well, there's kind of two aspects to it that I want to talk about. The first is that expressive types constrain the set of programs that you can actually write down. We kind of already know this, but just want to throw it out there on the table. So imagine that we have a type that looks like this, something that takes two lists of integers and produces a list of integers. If you just kind of close your eyes and imagine what that function could be, it could be a lot of stuff, right? You can imagine it's an append function, which is, you can imagine, going to be the punchline in a second. You can also imagine that it's a function that takes two arguments, returns the first argument, maybe returns the second argument, maybe it just adds the two elements of the list together pairwise. Who knows, right? If we add a richer type, we cut down the space of possibilities quite simply. If I make the type polymorphic, then I can't actually create a function that adds up the elements of a list because add is not a supported function or a supported operation over polymorphic variables. I can constrain the type even further to get kind of the result that we're probably all thinking we should get. If I constrain it with a dependent type, and this is probably the second time I guess we've seen length index vectors, so congratulations workshop. Then we're pretty much more or less forced to have the append function. All right? And so richer types allow us to constrain the space of programs. Dually, it also has the effect of allowing us to be able to develop programs in an incremental fashion, more or less mechanically. And I'm just going to walk through this for a very simple example, just so we kind of remember how this works. And all that kind of jazz. And so imagine I'm trying to write down this function that takes two lists, returns the third list. It's probably append. But nevertheless, just pretend we don't know what append is. If we just stare at the type, well, I know I need to fill that function or that definition in with something of that type. If I don't have anything in the context, I don't know if I have any other helper functions or things available to me, then the type demands that I have a function there. So I might as well just start writing down a function. All right, so I have a function that takes two arguments, and now I need to fill in the body. What could that body be? Well, like I mentioned before, we could put in L1, we could put in L2, but you can imagine that function doesn't feel right somehow. We're not really taking advantage of both arguments if we do that. But just looking at the type alone, we don't know what's going on. We need a little bit more information. And so in addition to the type, we might have some examples in mind. For example, we have two examples of, I see a surprise, it was the append function. And so with those two examples, we can refute these two possibilities for completing our function. Namely, the second example clearly is not L1 or L2 in that case. We have to do a little bit better. And so the way we do a little bit better is we need to get more information out of our parameters. We do that via pattern matching. And so let's go ahead and pattern match on L1. Could have pattern matched on L2, but we'll get to that in a second. And so if we pattern match on L1, because it's an algebraic data type and it has a finite set of cases, we can break it down. And so now we have to fill in the bodies of two function alternatives, one where the first list is empty, the second when it's not empty. The first example pretty much tells us what the first case should be. I should fill in L2. All right? The second one's a little trickier. All right? The way that I can sort of break it down is if I look at my second example, I know that, oh, by the way, if I get into that second example or second function case with my second example, I know the following things. I know x is bound to 0, I know xs is the list containing 1, and I know L2 contains the list containing 2 and 3. And what I need to construct is the list containing 0, 1, 2, and 3. And so with a little bit of teeth gnashing, we can probably figure out that what I need to do is cons together the results of a recursive call where we pass in xs and L2. All right, and that gives us our completed output that we want, and we can verify that by looking at our example. And so that's all well and good, but I argue that statement is just false. Right? My program did not write itself. It was a really simple function. We could all do this blindfolded sleeping or whatever, but we had to put in quite a bit of thought in order to make that happen. The types helped. Like, no one can deny that, but it wasn't enough. the whole point of this work is, can we actually get there? Can we make this automatic? Or can we make it semi-automatic? And that's really the punchline, all right? And so to answer the first thing about whether we can make it automatic, that's what I was doing before I started this work. And so previously I was looking at how to do program synthesis using type-directed programming. I'm not going to burn time today talking about it, but I'm just going to give you a brief sketch of how the whole dealio works, and then you can sort of check out some of our papers from before if you want to see the details. In essence, we do three things. We start out with a standard type system, and we recognize that type system, it is a relation, so there aren't inputs and outputs, but if we think of it as having inputs and outputs, the type is more or less an output to the relation. Well, if that's the case, then program synthesis just means we need to output a program instead of the type. So let's just flip it. And so the gut of the work is sort of how do we actually flip this typing judgment to turn it into a synthesis judgment? And it turns out it's a pretty mechanical transformation. Of course, that doesn't actually get us an actual program synthesizer. That gets us Greek and more Greek and things to prove. We have to do a lot more stuff to actually turn into a program synthesis system, something that actually does program synthesis in an efficient manner. And so that's sort of the precursor of this. And this is basically doing type-directed programming in a fully automated way, which, sweet, we did it. We're done. Close down the workshop. We got it. However,
What's X?
what's X? Oh, those are examples. Just Greek. Don't worry about it. However, I should also mention, there's kind of two parts to this. Our program synthesis system that we developed basically does two things. It does fully automated type-directed refinement of examples and types, and then also at the end of the day, it does some program search via blind enumeration that I'm going to get into shortly. But that's sort of the basis of the work, but there's some problems with it. Obviously, this is not the end of the road, not by a long shot. And so there were sort of two major problems with the work, at least as it stands so far. The first is scalability. All right? As you can imagine, we're not synthesizing all programs. We all still have jobs. So, you know, the problem is that programs are really complicated. In particular, there's lots of possibilities for programs that a synthesizer has to explore. We just saw one just now. I could pattern match on the first argument or the second argument to append. And a program synthesizer just doesn't know which one to do. And so it has to explore both. And in general, there's lots of those possibilities to explore. Another dimension is library functions, which we completely ignored. Well, if I'm looking for a function from list of A to list of A, well, there's at least 4 functions in the Haskell standard library that does that, and probably pretty more. I need to try all combinations of those and all compositions of those to see what works. And that just takes a lot of time. The other problem is that types and examples, while a reasonable form of specification, sometimes you have to have a lot of examples to push stuff through. And that was one of the weaknesses of our prior work. And so we're spending a lot of effort trying to figure out how to directly address these things. But let me posit something that might be just a little bit simpler to do. Why don't we just ask the user to help us? And so rather than talking about fully automated type-directed programming, maybe we can just build some tools to make type-directed programming easier for a developer sitting at the table right now. And so the way that we're going to do that is, let me tell you about one of the internal data structures for our program synthesis system. It's called a refinement tree. And so it essentially acts as a cache for all the programs that the synthesizer explores during the course of creating a program. We can break it up into 2 parts. The first part is these blue boxes, and these are introduction form refinements. Introduction forms are taken from bidirectional bidirectional type checking, rather. And so the essence of it is that some of the programming constructs in our language are determined entirely by types and examples. The example that we saw, when I started with the append function and I had a function type, I knew I'm more or less forced to put a function there. No questions asked. I can't put a tuple there or something like that. And so all of these are relatively easy to compute, and we can kind of blast them out more or less instantly for any specification given to us. The hard part are elimination forms. Things like function application, variables, pair projection, and so forth. All of these, you can't look at a pair projection and know immediately what the type is. You need to look at the context, you need to do some type checking, right? And because of that, we're forced to enumerate all such things. And this is sort of the heart of the scalability issue for our current system, is trying to keep down the number of terms, of which there are an exponential amount, that we have to explore during the process of synthesis. And so, it turns out that while this is a cool data structure for being able to factor out the cheap part of synthesis and the expensive part of synthesis, we also hypothesized that, hey, it might actually be an interesting thing for a programmer to actually manipulate and use directly. And that's what I want to demonstrate to you today. And so me and my students this past summer implemented a prototype proof of concept for a type-directed system based off of this data structure, and it's called Scum. I'm going to preface this by saying I don't use Emacs, so bear with me. All right. And so also I switched to OCaml. The tool's implemented in OCaml, even though all examples were Haskell. I apologize for that. I have two data types here, one for natural numbers and one for nat lists. And so what I'm going to do is I'm going to go ahead and remember the shortcut. It's not Vim. It's killing me already. To enter in some examples. And you can't really see it down there, so I'm just going to narrate it. So what I'm going to do is I'm going to provide to the tool some examples. So for example, I'm going to create a function called stutter. It's a function that takes a nat list and returns a nat list. And now it's asking me for examples. I'm just going to kind of enter them in incrementally. You stutter the empty list, you get the empty list. You stutter the list containing, oh, nope, I screwed that up. And that means syntax-wise, I might have to redo this, but let's just see if I can get this right the first go. So you stutter the empty list containing one element, you get that element duplicated. Have to check errors, don't we? Or check our examples. And then when you stutter the list containing two elements, you get a list containing four. And so I can go ahead and, assuming I don't have a syntax error here, cool. Let me drag this over. And so what the tool allows us to do is actually just that refinement tree that we saw, it allows us to incrementally build it and manipulate it. And so right now we have our current skeleton for stutter, which is blank. That's what the box with the bang inside means. And the tool figures out what are the possible program forms that I can fill in that hole with based off of the type in the examples. So in particular are two. Let me make sure I get this right. Oh gosh. Sorry. There we go. All right. I had to get my thumb on the meta key. And so I can either fill in a function, as you'd expect, or I can immediately try to guess an elimination form, of which there are none. So I'm going to go ahead and just guess a function. There we go. And so by doing that, now if you look above, you can see that I have a function filled in, and now I have a hole for filling in the function. I have a few choices for that based off of the examples that are given. I can either pattern match on the argument, or I can just try to guess. Guessing would result in failure because I only have n1. And so I can go ahead and expand the pattern match. Now I have two things I need to fill in, the nil case and the cons case. Of the nil case, I can fill in nil, and that's forced because the one example I have for when the list is nil is nil. And so I can go ahead and just select that through. And then for the cons case, it kind of runs off the side of the screen, so I apologize. But there are quite a few possibilities. And this is where this exponential blowup comes in. And so, for example, I can synthesize a cons. I can pattern match on the rest of the list. I can pattern match on the number. And I can also pattern match on the results of the recursive call, blah, 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 blah. We don't want to do that. And so you can sort of look at it and go, I probably want to cons on two things. So I'm going to cons on one thing. Now I have to fill in the cons. I know it takes a pair. Yep. And then go ahead and just kind of fill in the cons the whole way through. And you kind of see there's a whole bunch of possibilities. These are sort of things that we need to work on pruning. There are obviously things that we shouldn't consider at all and things that should be prioritized over others. And so I can go ahead and synthesize the second cons for stutter. You kind of see, doot. There we go. Oh, there. And so the final kind of skeleton I'm going to use is two conses where I need to fill in those conses with some variables and function applications. And then just to kind of kill it, the synthesized key is meta k for the record. Doesn't really work at all. And so after doing some rounds of guessing, we actually get the final result that we want. And so that's sort of how the tool works. Just to kind of close real quick, it's just a simple prototype. My students this summer just kind of took my synthesizer, hacked it apart to get what you saw there. But one of the things I'll just immediately throw out there for suggestions, and I'm really more than happy during Q&A or afterwards to hear your suggestions too, is live editing. So that was essentially just kind of a wizard. It'd be much nicer to be able to have like an IntelliSense type thing to it. But unlike type checking, which is actually really exciting for me, there's a whole bunch of kind of hard engineering stuff and theoretical stuff at play. In particular, for an IntelliSense engine, if you kind of type in some stuff and then the user enters in more stuff, you just type check because it's quick. Synthesis is not quick at all. And so we need to actually spend a lot of time thinking about how we can cope in the face of user edits and errors. As well as some other things too, such as being able to visualize types and examples as we're going through the program, and also integrating kind of automated synthesis to it. And so that's about it. Just want to show off, these are the kids that worked on that tool that you just saw, at least the 3 over there. And you can kind of check our project website if you have any questions. Thank you for your time. I'll go over here.
And can the next speaker come up straight away, because we had a problem with the slides. Questions? Yep.
So do you, oh sorry.
No, that's good, that's good. I don't want to listen to Richard, it's fine.
So I was wondering if you could explain a little bit more, if you re-type check the program every time you refine the program, or is there something behind the scenes which allows you to justify theoretically that if you combine the plugins with the refinement in that whole, you're
Yeah, that's kind of the core of our synthesis system, is that we can refine things and keep things well typed. It works in essentially kind of a decompositional style. I should have mentioned that the walkthrough that we did of Stutter, I did that because that's exactly how the synthesizer actually works, minus all the theory and such. Yes.
Can I ask a follow-up?
Yeah, sure.
How do you represent the holes then in there, where you have dependencies, the whole activity depends on bound variables which are introduced by, for example, the pattern. And maybe some outside variables, and some of the variables in the pattern might overshadow the previous variables and so on. How do you represent the dependencies of the whole on these kinds of variables?
So to the shadowing part, we completely sidestep that by injecting fresh names. We don't try to do any sort of fanciness there. For kind of free variables, they're just treated as library functions that can be synthesized when we're trying to generate function applications, and that's one of the problems that we run into as far as scalability goes. And then as far as independence, we actually make it so that the branches are independent. And for recursive functions in general, there's some weird theoretical stuff that we need to fix as part of future work. I'm more than happy to talk about that offline, because it's a giant rabbit hole.
Okay.
Oh yeah.
The example that you went through had examples of stutter. Because the user has control over choosing the branches, do you need the examples?
We needed the examples to justify. Certainly, we could just kind of thumb through every possible program that type checks, but that's a lot of stuff. And so the examples refine the set of programs we need to present to the user. So in the nil case for stutter, we don't have to present, oh, by the way, try doing a recursive call in the nil case. We can just show you the nil case and that's it. So the examples do some effect of refining things. And in general, for example, the cons is there. We weren't presented the opportunity to put nil in because the examples were refined to a cons at the top level. Yeah.
So is there any thought of putting counterexamples in?
That was our couple work, actually. Counterexamples are tricky from a kind of theoretical perspective. We sort of did a sequence calculus style interpretation of our work to be able to justify counterexamples using just kind of negation. I haven't tied together this sort of semi-automated work with that yet, but that's actually an interesting point of view because this is more interactive. One might expect to be able to do that and get some tangible benefit.
That would definitely pull your tree pretty nicely.
Yes.
Do it right.
Exactly. Yeah. Good.
So, get way more information if you have richer types, and your prototype is really on just about the simplest polymorphic language calculus.
It wasn't even polymorphic, I'll be honest with you.
Okay. So, I mean, have you tried to build anything with more complicated types?
We're getting there. So polymorphism was next on our docket. There's little technical complications with that. And we're actually sort of chained to OCaml at the moment. I'd like to be able to move over to Haskell and kind of tackle other things. But yeah, that's sort of, this is mostly just about like what a semi-automated experience would be like. Other part of my research agenda is kind of exploring the core techniques on extended type systems.
I have one more question.
Yeah, sure.
So not only examples, but sometimes you might know some laws about the function you're trying to, so have you considered, using examples and laws?
Yes, well, so other people in the synthesis space have actually. And so there's lots of work on kind of properties. We do types. Some people have laws for being able to restrict the space of things you have to enumerate. No one's really combined that yet to see, oh, can we actually synthesize something crazy new if we kind of put all the secret sauces together in the pot. And so yeah, definitely, for this tool, I'd definitely like to start trying that at some point.
So I think we need to stop there, unfortunately, even though there are lots more hands. But thank you very much.